For part 2 of the equations, we're going to solve quadratic expressions. So we're going to do the same process that we did in the first case. Step 1 is we're going to isolate the absolute value, which is already done here, obviously, and then I'm going to split it up into the two cases. So I'm going to have case 1, and I'm going to have case 2. Alright, so case 1 is the positive. X squared minus 3x is equal to 2. Case 2 is going to be the negative. Negative x squared minus 3x is equal to 2. For case 1, I'm going to say that we'll have x squared minus 3x. And I'm going to move that 2 over to get negative 2 is equal to 0. At this point, I can try factoring, but I'm going to find that factoring doesn't work. So either I have to use completing the square or quadratic formula. If I do either method, in this case I'll do quadratic formula, and then I simplify my quadratic formula, I find that I get x is equal to 3 plus or minus the square root of 17 over 2. I can take the positive or negative version of that, so the 3 plus root 17 over 2, or the 3 minus root 17 over 2, and find that x is going to be approximately negative 0.562 or 3.562. Now I'm just going to use these values to verify graphically with my calculator. In the second case, I would state that negative x squared plus 3x is equal to 2, which means that negative x squared plus 3x minus 2 is equal to 0, or x squared minus 3x plus 2 is equal to 0. This one I can factor. I'm going to factor it into x minus 1 and x minus 2. So in this case, x would theoretically equal positive 1 or positive 2. Now I'm going to graph the function out, where I'm going to say y1 is equal to my left side, y2 is equal to my right side. And when I graph it out, I'm going to have my quadratic function. And I'm going to have my linear function where it is equal to 2. And I can see that it has 4 points that cross here. In this case, if I check the 4 points, I'm going to have the one over here, which is going to be negative 0.562. This point is going to be when it's equal to 1. This point is going to be when it's equal to 2. And this point is going to be when it's equal to 3.562. So all of those solutions work. For case 2, once again, my absolute value is already isolated, so I'm going to say that case 1 is going to be the positive. X minus 5 is equal to x squared minus 8x plus 15. And case 2 is going to be negative of x minus 5 is equal to x squared minus 8x plus 15. If x minus 5 is equal to x squared minus 8x plus 15, I'm going to subtract x from both sides. I'm going to add 5 to both sides. 0 is equal to x squared minus 9x plus 20. I can factor this and get x minus 4 and x minus 5, which means that x would equal theoretically either 4 or 5. For case 2, I'm going to state that negative x plus 5 is equal to x squared minus 8x plus 15, and I'm going to add x to both sides and subtract 5 from both sides. 0 is equal to x squared minus 7x plus 10. I can factor this down. 0 is equal to x minus 2 and x minus 5, which means that x would either equal 2 or 5. Well, I know that I got 5 in both cases, but I'm only going to include the 5 from my original function so that I'm not including the invariant point twice. So I'm going to call that extraneous or unnecessary. I don't need to state the 5 twice. Then I'm going to graph this out and check and see what it looks like. Well, I'm going to wind up with my quadratic function on the right-hand side is going to look something like this. I have my absolute value function on the left-hand side is going to look something like this. And then I can see that it has 2 points where it crosses. I have one here, and I have one where it hits right at the vertex. And this one occurs when x is equal to 2. And this one occurs when x is equal to 5, which means that I have an extraneous root of 4 here. Where would that extraneous root actually exist? Well, if this line for the positive version kept continuing on in this negative direction, then I would have theoretically had that point hit, but because it doesn't, that's where my extraneous root was created. All right, now I have my last case, where if I have the absolute value of x minus 2 is equal to the absolute value of x squared minus 4. Well, I'm going to say that for case 1, then I'm going to have x minus 2 is equal to x squared minus 4. For case 2, I'm going to say that x minus 2 is equal to negative x squared minus 4. Now, we could theoretically state 2 more cases. I could have a negative for the first one and a positive for the second one. But I can see that that's going to be the exact same as this one if I just multiplied both sides by negative 1. So I don't need to solve the same one again. It's the same as if I said that I had both of them were negative. Negative x minus 2 is equal to negative x squared minus 4. Well, that would be the same as if I multiplied the first case by negative 1 on both sides. So I'm just solving the same thing again. So I'm not going to do that because of the redundancy. So I'm just going to solve these 2 cases. So if I said that x minus 2 is equal to x squared minus 4, then 0 would equal to x squared minus x, and when I add 2 to both sides, minus 2, which means that 0 is going to, when I factor it down, equal x minus 2 and x plus 1. Or x would theoretically equal 2 or negative 1. For the second case, I'm going to state that if x minus 2 is equal to negative x squared plus 4, then x squared plus x minus 6 is going to equal 0, and I'm going to get x plus 3 and x minus 2 is equal to 0. So here x would either equal negative 3 or positive 2. Well, like we saw in the last case, if I already have the same answer here and I have it again here, it's going to occur at an invariant point. I don't need to state it twice. So I'm only going to say that it's going to exist in my original version. I graph these out. So I'm going to put my left side is going to be one equation, and that's going to look something like this. I'm going to state that my right side is going to be the other equation, and that one is going to look something like this. And then I can see that I have 3 points where they cross. One is going to be when x is equal to negative 3. One is going to be when x is equal to negative 1. And one is going to be when x is equal to positive 2, which are my 3 solutions there.